So here we're going to continue talking about sets. I'm going to introduce a couple of different concepts here. Now, the first one being about the universal set. So in general, we talk about sets A, B, or C, or whatever, but what we want to kind of define is this idea of the universal set. Right? So if we have some set A, B, right, we can define the union, the intersection, but all of these live inside of the universal set U, right? All of the possible elements of wherever we're taking elements from. Now, a way to think about this is when we're dealing with numbers, right? We deal with rational, integers, right? But those are all live in here. We can think of the universal set as being the set R. Okay, so that's one concept here of this universal set that encapsulates all of the elements that we are drawing from. All right, now another thing is this idea of a complement of a set. So if we think of just a binary relation, either an element is part of the set A or it is not, right? And if it is outside of the set A, the set that is not part of A, we call that the complement, right? So the way usually designated by this notation here, right? So the way we read that is the complement of A. All right, so if we think of, okay, we have here within our universal set, right, the set A, right? So A would consist of, right, just kind of if we're illustrating it in this way by a Venn diagram would be this, right? And the complement of A would be everything out that is not an A. Right? So everything outside here. Okay, so those are two kind of concepts here that we want to introduce when talking about sets, right? Just again, additional vocab as to how we talk about sets here. Now, we also have the set equivalent of De Morgan's laws. Right, where here and they're parallel with our logical equivalences here, where if we had, I think so for logical equivalence, we have the conjunction right here is parallel with the intersection, right? So the complement of that is a union of the complement of each individual set. And vice versa, the disjunction, the union, B is C, is equivalent to the intersection of each individual complement. Right? A complement intersect with B complement. Okay, so those are De Morgan's laws for sets. Now let's prove one of these, right? So we're going to prove this using our logical equivalences. So and again, we're going to be able to do this because of set builder notation. Right, so if we have here, let's start with this one, right? Or let's do this one, right? A intersection of B and the complement of this, right? So first, let's start off with here. This set is defined by X such that X is not in the intersection of A and B. Okay? All right, now using our logical notation here, we could say, all right, that means that, X is not in AB. So we could say not X element A intersection of B. All right, and now for these sets, I'm able to write the intersection, in this case, as a conjunction. Right? Sorry, disjunction here. So here we have X such that here we're going to negate this. X is an element of A, intersection of AB is logically equivalent to X is an element of A, and X is an element of B. Okay, and now here we use De Morgan's law for our logic here. X such that here we could say we can negate so here not X element of A or not X element of B. All right, and if X is not an element of A, then we say X is an element, not an element of A, and X is not an element of B. And in other words, X, if it's not in A, then it is in the complement. And if it's not in B, then it's an element of the complement. And we have our desired result here, right? So X is an element of the complement and the complement of A and the complement of B. So that's A intersection of B. All right, so that is an approach here that we can take to proving one of De Morgan's laws. Now let's take a look at a different proof. Now this idea of subtracting or B, right, or removing or minus a subset, right? So we're going to prove, so first of all, the notation, right, A minus B. So we can think of this as a set of, if this is A, this is B, right? So A minus B will represent any of the overlap here, right? So A minus B would represent these values here, right? Where you take away the values that are on both A and B. Okay? All right, so what I want to do here is I'm going to prove that if A and B are sets, then A minus B is equal to A intersection of B complement. Okay. And again, I'll approach this in the same way using my set builder notation, right? So A minus B consists of elements X such that X is an element of A and X is not in B. Okay? All right. Okay then, so now from here, we can say, all right, if it's not in B, then we can say, all right, well then it must be in the complement. So X element of A and X element of B complement. Okay, well here it just is, I can rewrite this if it's both, so it's an intersection, right? Element of A intersection B complement. All right, and now we have A minus B is equivalent to A intersection B complement. All right. All right, now there's an alternate approach here if you don't like the set building notation. And another way to approach this right? So the way that we show, just in general, right, we can say that two sets are equal, right? Again, just in general here, and actually let me, before I do the alternate proof, in general, an approach that we can take to show that A is equal to B, we could show that A is a subset of B, and then show that B is a subset of A. Now, if you show this, right, A is a subset of B, B is a subset of A, then that leads us to the conclusion that A must equal to B. Okay, so that's one way that we could take this. All right, now an alternate approach using this, right? So an alternate approach for proving that A minus B is equal to A intersection of B complement is, all right, we want to show that A minus B is a subset of A intersection with B complement. Okay, and again, the way we would do this is, all right, so by definition, we let X be an element, or by assumption, we'll let X be an element of A minus B. Okay, and what does it mean for it to be an element of X minus B? So by definition, right, X is element of A and X is not in B, right? That's what A minus B means. All right, and then furthermore, right, if it's not in B, by the definition of a complement, then we could say X is an element of A and X is an element of B complement. Right, now here, right, our conjunction here leads us to believe, well, if both of these have to be true, then it has to be part of the the intersection, so X must be in the intersection of B complement. Okay, now again, this just shows that A minus B is a subset of the intersection, right? Now we have to do, in order to complete the proof, we have to go the other direction, right? So now we let X be an element of A intersection of B complement. All right, and a very similar proof here, right? But the only thing here is we start on this end where we say, all right, so we let X be an element of the complement. So what does A intersection with B complement? So what does that mean? All right, it means that X is an element of A and X is an element of B complement. Okay, all right, and then here, just applying our definitions here, what does it mean to be in the complement? Right, it means that it is not in B. Okay, and the way we define this is that X is an element of A minus B. All right, and now we have shown that A intersection of B complement is a subset of A minus B. But A minus B is a subset of the intersection of A and B complement. So therefore, our conclusion here is that A minus B is equal to A intersection of B complement. All right, so here's just an alternate approach to the proof, right? Where in general, this will work if you want to show that two sets are equal, show that they are subsets of each other. And the logical conclusion is that they must be equal to each other.